The second thing which we can pick from this table 12.2-1 are these three seismic design parameters. First is very important, response modification factor R for your particular structural system. It is also called the behavior factor in Eurocodes. The second is the overstrength factor omega, and third is the deflection amplification factor. These three are the seismic design factors: R factor, omega naught, overstrength factors, and third is the CD factor, deflection amplification factor. Once you know that a particular structural system is allowed or permitted in your seismic design category, then you pick these three coefficients or three factors from this particular table for your structural system. So let me quickly explain one by one these three factors. So let's say that this is your structure, your multi-story building, and then you model it in a particular structural engineering program, finite element based program, and it is an elastic structure, for example. Elastic structure or elastic model, which means that it is following this basic equation F is equal to Ku, that as we increase force, applied force on this structure, the resulting displacement is increased by the same proportion. So the force and displacement, they are related by a constant quantity called the stiffness of this structure. And the K matrix is already fixed constant matrix formulated by the finite element program already. Let's say that we perform one exercise, and that is that we take a pattern of loading, a very small loading on first floor, higher loading on the next floor, more higher, and then keep on increasing the loading, and the values of these loadings we increase with the same proportion such that the pattern remains same, and we apply those forces, let's say F1 up till Fn, right? The reaction which this building is going to develop at the base will obviously be the sum of all those forces. So if you apply equilibrium, the reaction you get at the base should be equal to summation of Fi, where I is equal to 1 to n. Let's call that reaction as base shear, V. So V is the base shear, or in other words, it is the sum of all those applied forces, right? If we do this exercise, that we keep that pattern constant but apply an increment to these forces, which means we keep on applying a factor to these forces. So forces start with a very small value and then keep on increasing, and resultingly the deflection of the roof, let's call it U roof, UR. Let's keep on noting or checking that roof displacement. So every time I apply an increment to this load pattern, I get the resulting UR. I increase the forces more and I get a higher UR. If the model is elastic, the resulting relationship between sum of all the forces on y-axis, which is equal to V now, and the UR, the relation between these two quantities will obviously be linear forever, right? So V is equal to summation of I equal to 1 to n Fi. So all the applied forces, their total summation is on y-axis, and the resulting roof displacement is on x-axis. So I start with a very low value, then I apply an increment to forces, I get this point. I apply another increment, I get this point, and this will be a straight line forever because our structural model on which we are applied this loading pattern is elastic, so it is following F is equal to Ku, so linear relation forever. Now let's say that on the same graph, let me make it a bigger graph, V versus UR, and let's say we perform that experiment and we get a straight line, which is this straight line, right? So it is still keep on going up, but and it will go forever. Let's say that the equivalent static forces, the representative forces of the future earthquake, because we can convert approximately the effect of earthquake into some future, into some equivalent static loading, which will obviously have a very similar pattern because they are mass proportional. So they will deflect the building in this manner, which this particular pattern is going to deflect. So let's say that the equivalent static forces which the future earthquake can produce in our structure are on y-axis. Let's say they are somewhere here. So this number is what? This is the equivalent static forces, which means that these are the forces which the future earthquake will produce. So let me just write it somewhere here. Future earthquake will produce, right? So correspondingly, obviously, if this is the level of forces which is expected to be produced by future earthquakes, correspondingly this will be the deflection. If I come down here, this is the UR value on x-axis which my future earthquake is going to produce, right? Now, for two important reasons, it is not wise to design your structure on these forces, this number on y-axis. Let's call this value as V elastic. V elastic. This is the value of base shear or the sum of all forces which your elastic structure is going to produce in case of the future earthquake, or these are the forces which should be applied to your elastic structure uh, in case to represent the future earthquake, right? So I was saying that for two important reasons, it is not adequate or wise decision to design your structure on this V elastic, right? If, for example, what we do, we apply these forces F1 to Fn, we apply we apply such that they are equal to V elastic, and we can perform all the design calculations and calculate the cross section size and reinforcement in our building. We will give a capacity to our structure to follow this linear line up till this particular point, starting from origin up till this particular line. So if we design on V elastic, which means we apply V elastic force to our model and calculate reinforcement based on that, we are actually asking our structure to follow a linear line from origin to this particular point A, right? Because the structure will have the capacity to resist V elastic because we design on V elastic. So our structure will follow that straight line OA, right? But for two important reasons, we may not design our structure on V elastic. We may design our structure for just a fraction of V elastic. And those two reasons are, number one is the inherent ductility. So ductility of our structure, ductility, and second thing is the overstrength. There was a time when we were designing our structure in past times, we were designing it on V elastic, right? But later on we realized two important players which can play a very important role in the seismic design. One is called ductility. That structure have a beneficial, you can say, beneficial kind of property in it, which we can use to economize our structure. And second is the overstrength. Overstrength is the property that structure exhibit the capacity or strength more than the designated strength. It starts from material overstrength up till cross-section overstrength, then member overstrength, and finally structural overstrength. From material overstrength, you can easily guess that if the concrete FC prime is 30 megapascal, the actual FC prime may be 35, for example. Similarly, if the steel Fy is 60 ksi, the actual Fy can be 70 ksi. So the overstrength originates at material level and then it propagates to cross section, member, and then full structure level. Similarly, ductility also. Ductility is a property to withstand the deflections without significant failure. So it is the property which is very useful, that in different past earthquakes it was actually observed that if a structure is designed on a force of 100 kilonewton, for example, and if an earthquake occurred which can produce potentially a force of 125 kilonewton, it was observed that the structure still was able to sustain that force higher than what it was designed for. And the reason was this factor, ductility, that structures have the capacity to accommodate large deflections without significant failure. So we can use these two useful properties of the structure to reduce our design forces from this V elastic. So the idea is that we don't design our structure on V elastic. We design our structures on a fraction of V elastic. Let's call it V design, and let the ductility and overstrength play its useful role. So we provide the capacity not corresponding to V elastic. So we don't apply nowadays V elastic force and then design based on that. We just apply V design, which is around 1/4, 1/5, 1/6, or it can be even 1/8 of the V elastic, right? And then we design on these reduced forces, give the capacity based on these reduced forces. So our structure is given a capacity up till this point to remain linear, and beyond that the structure is allowed to go into non-linear range, right? Because of the overstrength, it will not just yield and become flat at this point. In real earthquake case, it will show some overstrength, right? Some overstrength beyond the point at which it was designed. And at the same time, the ductility capacity will not let the structure to collapse or have significant damage up till the design level earthquake. So if we design on V elastic, our structure will follow the straight line from O to A. So V elastic, our structure in real earthquake, it will follow a line OA. But if we design on V design, which is significantly lower than this V elastic, the structure will follow this line O. Let's say this is the B, and from this B point onwards, OB will be linear. Obviously the structure have that capacity, it is designed on V design, so it will remain linear up till OB, but beyond OB it will deviate from the straight line, it will show some overstrength, and it will exhibit whatever ductility it has. So it will follow a new line, this bold line for example, and it will reach to a new point, let's call it C, right? So if a structure is designed on V design, it will follow O, B, and then C, right? So the idea is that we design our structures on a value of force which is significantly lower than what is required for the structure to remain elastic in the design earthquake. So we don't want our structure to remain completely elastic for the full design earthquake. We want it to remain elastic up till certain level of loading, beyond which it can be safely allowed to go in non-linear range. So BC is actually what? It is an intentionally allowed non-linear range in which the structure will exhibit its ductility and the structure will exhibit its overstrength. So relying on these two important useful properties, we let the structure go in non-linear range, but at the same time we bring economy in our design, that instead of designing on V elastic, we design on V design. And the ratio between V elastic and V design, these two levels is actually this R factor. So an R value of 2 means that we are designing our structure on half of the forces uh, which are required for our structure to remain elastic during the design earthquake. So R value of 3 means that we are designing our structure on 1/3 of the forces which are required for our structure to remain elastic. So this is the concept of R factor. So which means that if our structure is brittle, R factor will be close to 1, which means that we cannot take advantage of the ductility of our structure. It is already brittle. So we have to design on a higher force, V elastic, and the cost will be more. If we make our structure more ductile, which means we can more rely on its ductility, and which means we can reduce the V elastic to a very high level. Actually, we can reduce it more. So we bring the design forces more down and bring economy in our structure. So this is the concept of R factor. So it is the ratio between V elastic and V design. V elastic and V design. So this is R. So now one important thing is that since we design on a lower value V design, which means that when the seismic forces on our structure in actual will go beyond this V design, the structure will exhibit nonlinear behavior. So sometimes this V design is also called as V inelastic. V inelastic, because this is the level from which the inelastic you can say behavior starts. Depending upon the overstrength, uh, the line BC may have different slope. Sometimes it may directly go flat, indicating no overstrength, and sometimes it may exhibit some overstrength. So R is the ratio between elastic base shear and design base shear. Or in other words, we can simply reduce the elastic base shear V elastic with the R value. So V elastic can be divided by R value to get the V design. So V design is what? V elastic over R. The more ductile our structure is, a higher R value we are allowed to use. If we focus more on the detailing and confinement requirements and everything and qualify for the special moment resisting frame, an R value of 8 or 8.5 can be allowed by the building code. But if we don't care about the seismic detailing, an R value of 3 or 2 may be recommended by building code. So it's all about economy and ductility. You focus more on the ductility, the more economy you can bring in your structure. For brittle structures, the code will recommend a higher design value for the design. It depends on what capacity we give to our structure, right? So it's the question should be always coupled with how much capacity we provided. So if we design our structure for V elastic, it will follow OA line, right? So if we provide the cross section sizes and reinforcement amount such that the forces applied were V elastic, then the structure in actual will follow OA line. But obviously that design will be very costly. So the decision is yours. Either you let your structure completely elastic during the design earthquake and get a costly design, or you design your structure on a fraction of the V elastic value and let it go into nonlinear range, which is OBC. But obviously you cannot just decide on your own. You have to particularly make sure that your structure can withstand deflection safely. So if you focus on ductility, you, for example, pass all the requirements of the special moment resisting frame or intermediate moment resisting frame, etc. Only then the R factor from the building code can be applied. So this reduction on the bottom left from elastic to design value by the R factor, this reduction is coupled with the fulfilling the requirements of different structural systems. So this will be 8 if you fulfill the requirement of SMRF. So if you previously were designing your structure on 800 kilonewton, now you just apply 100 kilonewton and provide the reinforcement. So you will be very economical, but at the same time you have to follow the SMRF requirements and guidelines. If you go for OMRF, this R may be 3 or 4 maybe, right? Or resultingly, your design values will be very high. You will end up in a very costly design, but then you don't need to care about the seismic detailing and everything, right? So this reduction by the R factor from V elastic to V design is coupled with fulfilling the requirements of different structural systems. So again, I repeat the answer of your question. Whether your structure is going to follow OA or OBC, it depends on what forces you apply for the seismic design, on what forces you design your structure. If you design on V elastic, higher forces, your structure will follow OA. It will not even crack, but at the same time, the design will be very costly. And at the same time, you don't need to worry about the seismic detailing and ductility and everything. But a more wise decision would be to design our structure on just a fraction of V elastic, design our structure on V elastic over R. In that case, our structure will go in nonlinear range in the design earthquake. It will follow OBC, but then we can rely on ductility and overstrength of the structure. We can make sure the structure can sustain that nonlinearity in a safe, you can say, manner, right? So that's how R factor plays a very important role in seismic design, whether it is ELF procedure, RSA procedure, or this linear time history analysis procedure. So in all three seismic design procedures, this R factor will have its role. Now it will have its role, and the reason is that the computer model which is used for the purpose of seismic design is elastic model. If we can actually make it non-linear, just imagine for 1 second that we have a non-linear computer model, then we don't need this R factor. Our structure will automatically follow this OBC or any line, whatever will be the real line depending upon the capacity of our structure, right? So this R factor is there because we are using a linear elastic model which cannot capture the inelastic behavior. So therefore we simply first calculate V elastic, divide by a constant number R and get the design V, right? So this is the use of this R factor. Building code is recommending a linear elastic model for the seismic design which cannot capture the effect of cracking, yielding and everything. So in order to bring down the elastic V to some design level, it just recommends a constant value R, and R is made a function of the structural system, SMRF, OMRF, dual system or any other system. So from the same table 12.2-1, you will pick not only your structural system which is permitted, you will also pick this R factor associated with that, and that will be playing its role in all three elastic analysis or elastic model based seismic analysis procedures. But if you perform nonlinear time history analysis and your model is nonlinear, then there is no need of these code based seismic design parameters, no need of R factor, because whatever capacity is in your structure, the model will be able to follow that line. It will not be essentially following a straight line as the elastic model will do, right? Actually, when I say that the structure follows OBC, it means that this is the level of roof displacement which your future earthquake or design level earthquake is going to produce, right? So the O, B and C, this is the path which the actual structure is going to follow if you design it on V design. But OA is the path which it is going to follow if you design it on V elastic, right? So at point C, your structure, this is the last point, which is the roof displacement corresponding to point C is the displacement produced by the future design earthquake. So imagine that this is the level of future design earthquake and we are not going beyond that, right?